Hi, everyone, and welcome to today's Smart Chart webinar focused on LA-ICP-MS. Our presenter today is Dr. Andrew Zipkin, Associate Scientist here at Eurofins EAG Laboratories. I am Dina Ingram, and I am part of the marketing team here at EAG. Prior to getting started, I would like to go over a few housekeeping items with you. All attendees have been muted. However, we would still love to hear from you during today's presentation. You will have the opportunity to ask text questions by typing your questions in the questions panel located in the bottom right corner of your screen. You may send your questions at any time during the presentation. Our tech expert, Dr. Das, who will be answering some of these questions during the presentation and others will be addressed during the Q&A session at the end. At the end of the webinar, a brief survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now I will turn it over to our presenter, Dr. Andrew Zipkin. Andrew?
Hi there, everyone. So thank you, Dina, and just a little bit about me to get started, folks. Wherever you're joining us today, thank you for being here. My academic background is in biology, archaeological science, and isotope geochemistry. I've been doing laser ablation in the context of those fields for over a decade. In 2021, I transitioned from an academic career to industry and joined EAG Material Sciences. Outside of EAG, I maintain my status as a registered professional archaeologist and serve on the board of 2 professional societies. So this presentation is geared towards individuals and organizations that have some familiarity with data derived from elemental analysis by mass spectrometry, but little or no experience with laser ablation in particular. So by the end of today's webinar, we will have concisely addressed the fundamentals and history of laser ablation, its capabilities, its pros and cons relative to a more traditional solution ICP-MS, and walk through a complex LA-ICP-MS project from sample prep all the way through to data analysis. And at the end there will, of course, be a Q&A, as Dina noted. But first, a little bit about Eurofins. Eurofins is a global leader in testing with more than 61,000 employees and 940 laboratories in 59 countries. EAG Laboratories is a division of Eurofins, specializing in materials testing with over 40 years of experience. We have more than 600 highly educated and skilled employees who use state-of-the-art instrumentation and know how to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. With 16 laboratories and 5 business development locations around the world, we serve more than 4,000 industrial, governmental, and academic clients. Today, I will speak about laser ablation ICP-MS from the perspective of our Syracuse, New York, USA facility where I am based. However, I should note that we also offer extensive laser ablation capabilities at our Eindhoven, Netherlands laboratory. Let's take a look at our SMART chart to start. SMART is an acronym for Spectroscopy, Microscopy, Analytical Resolution Tool. This chart represents available techniques at EAG graphically. Dark blue areas provide elemental information primarily, green indicates imaging information, and red a mixture of both. Now the x-axis shows the dynamic range for each technique from 1 angstrom to 1 centimeter. The y-axis shows detection limits, either in atoms per cubic centimeter on the left, or in concentrations from part per trillion to 100% atomic on the right. Laser ablation mass spec services as offered by EAG primarily emphasize elemental information ranging from high atomic percent concentrations down to tens of parts per billion. While there is no typical laser ablation job, my projects most commonly use a spot size between 50 and 100 microns in diameter to measure both matrix elements in the percent atomic range and trace elements in the hundreds to subpart per million range. Analysis distance into the sample has got a major influence on selecting the best technique for a given material and objective. The analysis depth of laser ablation is strongly influenced by the wavelength of the laser operating parameters set by the analyst based on experimentation and experience, the opacity of the target material, and whether the target is a cohesive solid or a pressed powder. While top-down depth profiling with laser ablation is possible, more typically depth profiles are measured in cross-section, such that depth becomes an X or Y axis relative to the laser. Let's move on to our first section, fundamentals of laser ablation technology. So let's start with the basics. Laser ablation is simply another ICP sample introduction method like traditional solution ICP-MS or variants like liquid chromatography ICP-MS. Like that latter example, laser ablation is a form of time-resolved mass spectrometry, in contrast to the steady-state signal of traditional solution ICP-MS. The most important distinguishing properties of laser ablation MS are: 1, the sample is in a solid state when analyzed. 2, the technique is microanalytical, only measuring a tiny fraction of material required by other forms of ICP-MS. And 3, following from the first 2 points, laser ablation is spatially resolved. Even when analyzing a homogeneous sample, you see what you shoot, and can thus associate spatial information, like XY coordinates, with chemical data. So how does laser ablation manage to introduce a solid sample to a mass spectrometer? The diagram at right illustrates the ablation process as it occurs over roughly a millisecond. So the top is 0 time and the bottom is about 1 millisecond after the laser is fired. So first, material is removed from a solid sample using a pulsed laser. It's not continuously firing, it's operating in bursts. The pulsed laser induces heating, evaporation, ionization of the sample. The plume of ions then recondenses back into particles, which are swept into the ICP-MS by a carrier gas stream. The argon plasma in the ICP torch ionizes the sample again for discrimination and measurement according to the mass-to-charge ratio of the positive ions. Now, laser ablation produces a transient signal, which can be treated as either a pseudo-steady-state signal for bulk analysis or as a time and spatially resolved signal for mapping applications. Now, this figure on the right from Gray 1985, which is the paper that actually introduced laser ablation as a technique, shows individual laser pulses. So on the bottom is the time axis on the x-axis, and response or signal intensity from the mass spec is the y-axis. So as you can see, the laser is pulsing, and each pulse induces a response in the signal. Now, with the preliminaries covered, let's look at a typical example of modern laser ablation instrumentation to see how this technique works in the lab. Starting from the top right of the diagram, we have a laser source that emits at a fundamental wavelength of 1064 nanometers, which is then frequency quadrupled to an ultraviolet wavelength of 266 nanometers. An aperture is used to set the beam diameter to the desired spot size. The beam is bounced off a mirror and targeted into a sample holder, or cell, with a movable stage. A video camera peering into the cell and connected to a computer is used to adjust the depth focus of the laser and to guide movement of the stage such that the desired area is ablated. When the laser strikes the sample, the ablated particles are swept by a helium carrier gas stream out of the cell and into the argon plasma torch of the ICP, where they are ionized. The ion beam is focused by the sampling interface and ion optics and directed into a quadrupole, where they discriminated among on the basis of their mass-to-charge ratio, as in other forms of mass spectrometry. Now, this is a general illustration right here. At EAG in Syracuse, we specifically use an applied spectra J200 tandem laser, which is also capable of laser-induced breakdown spectroscopy, coupled to a thermoscientific ICAP-TQ or triple quad mass spectrometer. Having covered the generalities of how laser ablation works, I'm now going to situate this technology in its historic context to show how we arrived at its present use. So laser ablation was first developed by Alan Gray at the University of Surrey in 1985 for geochemistry applications. Using laser ablation for mass spec occurred just 2 years after the introduction of the first commercial ICP-MS system, the Perkin-Elmer MDS SciEx Elon 250. Some further notable early innovations were accomplished by Simon Jackson, Henry Longerich, Greg Dunning, Brian Fryer, and Detlef Gunther, of which 4 of the 5 are pictured at left. And much of this work was done at Memorial University of Newfoundland in Canada. Now, I mentioned MUN for 2 reasons. First, Canada historically has had a rather strong mining sector and consequently invested in geoscience education and innovation, which in part explains the concentration of early laser ablation expertise at a Canadian university. Second, MUN is where I first learned laser ablation in 2011 and 2012 from the geochemist John Hanshar. So essentially, LA-ICP-MS was invented for academic geochemistry, but has since proliferated into a diverse array of fields such as forensics, archaeology, paleontology, biomedical science, industrial R&D and quality control, and failure analysis, to name just a few examples. So I'm going to emphasize just a few key innovations that shape how this technique is used today. We can hardly cover all of them in the time that we have, but these are some that are worth mentioning. So first, compared to the JK Type 2000 Ruby laser used by Gray in 1985, most modern laser ablation systems use either a solid-state neodymium-doped yttrium aluminum garnet source or an argon fluoride exaplex gas laser source. A second major development is the two-volume laser ablation cell. In order to be able to have larger cells that can hold more or larger samples without causing problematic delays between ablation and washout of ablated material, a conical cup or funnel moves within the cell to over the target location and siphons off the ablated particles. This not only reduces memory effects between samples, but is what makes laser ablation mapping possible. A third innovation is data reduction software. Processing raw time-resolved signal intensity was once extremely laborious, but since the early 2000s, graphical user interface applications like Glitter, Iolite, and most recently HDIP have made routine data processing simple while adding specialized capabilities like modules for chemical imaging, geochronology, and isotope ratio studies. Lastly, something we've been exploring at EAG is fully exploiting triple quadrupole mass spectrometry capabilities of our Thermo ICAP TQ. One project I am working on now is using oxygen reaction gas to mitigate the isobaric interference of rubidium mass 87 on strontium 87. Because strontium in the ablated material will react with oxygen in the reaction cell of the mass spec, while rubidium will not react, the two elements can be separated such that only strontium is ultimately measured. Now, looking ahead, there are two major near-term developments about which laser ablation users and consumers of laser ablation data should be aware. First, femtosecond lasers use extremely short pulse widths or pulse durations to minimize undesirable aspects of ablation, like elemental fractionation, thermal damage to the target, and imprecision in measurement. So these are still moderately exotic, but they are commercially available at this time. Another hardware development is on the mass spectrometer end of the equation rather than the laser. Instead of using sequential mass spectrometry, where different isotope masses are measured one at a time consecutively, time-of-flight MS offers functionally simultaneous data collection, which is ideal for measuring many analytes in the same analysis, and especially for chemical mapping applications. And you can see here on the right, this image from Toftwork, which is a manufacturer of time-of-flight mass specs. This is a concentration heat map of platinum in a thin section of a rat kidney perfused with the heavy metal-based anti-tumor drug cisplatin. And this is actually not a terribly exotic application. Biomedical applications like this are a quite common use of laser ablation chemical imaging. So let's move into our capabilities overview. We're going to cover some pros and cons of this technique, view different types of laser ablation patterns on a sample, and then conclude with some case studies. So first, we're just going to work through some strengths and limitations, pros and cons. So a major strength of laser ablation MS is that you can do everything from trace through minor through major elements in the same analysis. Quadrupole mass specs have got typically a pretty high dynamic range and introducing a really small amount of sample material, so you can do quite a bit in the same analysis. As I mentioned earlier, this is a microanalytical technique. Here at EAG, we routinely target sample features like defects or inclusions between 200 and 40 microns in size. We can go lower, but these are sort of the most common range of targets that we deal with here. As needed, you can collect uncalibrated signal data or just signal intensity in counts per second, semi-quantitative concentrations, or fully quantitative concentration data. Sample type is not constrained by conductivity, vacuum stability, inorganic, organic composition, or optical transparency or opacity. And finally, my favorite of these strengths is that relative to solution ICP-MS, this technique is relatively quite fast because there's no sample digestion step. There are no hours or days of microwave digestions or hot block digestions. The sample goes under the laser and you shoot it. For the same reason, it's a cleaner technique. There are fewer opportunities for contamination, no risk of trace metals in your test tube or of reagents that potentially are contaminated by the manufacturer. It goes directly in and it's analyzed as is in most cases. And finally, it's a relatively green technique. There's no hazardous waste generated and minimal consumables used. Laser ablation just runs off of argon, helium, and electricity. On the limitations front, Same problems as you have for solution ICP-MS. You cannot measure unstable radioisotopes, hydrogen, nitrogen, oxygen, fluorine, and noble gases are all out. Now, I mentioned before you can get uncalibrated semi-quant or fully quant data. Well, fully quant data does have some caveats. You can collect it, but you need to have matrix-matched solid-state reference materials for calibration. Now, by matrix-matched, I mean that the major elements present in the sample, so for example, nickel in an Inconel superalloy, should be present at similar concentrations in the reference material used for calibration. This helps to account for elemental fractionation effects and isobaric and polyatomic interferences, among other phenomena. Now, in addition, in order to acquire fully quantitative data, you need both a matrix-matched calibrant and an internal standard. An internal standard is an element, typically at high concentration, that occurs in both the samples and reference material at known concentrations, and which is used to correct for differences in ablation yield between measurements. The absence of either of these requirements will yield semi-quantitative concentrations, which cannot be directly compared to measurements obtained by other techniques. However, as we will see later, semi-quant data is entirely sufficient for solving some very complex problems. So now just to wrap up this slide, some other limitations. Large and/or regular samples may need mechanical preparation, so cutting, embedding an epoxy, polishing is needed in order to fit in the ablation cell and present a relatively flat surface to the laser. And lastly, samples do need to be stable at room temperature and free of liquid for most applications. There are some exotic examples like cryogenically chilled laser ablation cells, but those are mostly found in university and biomedical laboratories. Okay, so now we know laser ablation's strengths and weaknesses, but what does it actually look like on a sample? Here we see a piece of high purity tantalum metal with multiple ablation patterns in the form of scan lines, fixed spots, and a raster ablation pattern, moving from left to right across that image. So scan line ablations are typically used for replicate analyses of homogeneous samples. So that's pseudobulk analysis where you might analyze a sample 5 times and then calculate summary statistics from the results, or for measuring elemental gradients in a sample where you expect to see change over distance. So for a scan line, the sample is moved on the laser at a fixed rate while the laser pulses at a fixed rate. In this case, the Z or depth focus should never be lost, which gives you a nice, smooth, pseudo steady state signal. Spot ablations, as illustrated by those 4 different size spots or craters in the center, are mainly used here for targeting small features, so inclusions or defects. You can also lay them in a grid to make an interpolated chemical map. Now, for spot ablation, the laser pulses at a given rate at a fixed location, and as it ablates down, Z focus is lost. Finally, raster ablations. On the right of the slide, you can see it's basically a scan line, but it has switchbacks, so there aren't any gaps. It continuously ablates over a larger area. Now, the reason for this is that long duration measurements can improve precision. So for example, if you're doing an isotope ratio measurement where you need to have 4 decimal places of precision, or you can also use a raster for continuous mapping of an entire sample surface. So our first case study combines a classic target material for laser ablation, a silicate glass, with one of our most basic and commonly requested project types here at EAG, a good versus bad analysis. So a manufacturer of high purity quartz glass for the semiconductor industry detected a series of opaque inclusions in a batch of glass and needed to ID them to address the problem. They suspected that the inclusions were metal debris from the manufacturing process, but they also needed to rule out mineral impurities in the source quartz sand used to make the glass, such as the minerals pyrite, which is iron and sulfur, or uraninite, which is essentially uranium ore. So in this project, we measured the elements sodium, magnesium, silicon, sulfur, potassium, calcium, titanium, manganese, iron, barium, thorium, and uranium in these samples, targeting areas that are both away from the defect and on the defect. So spot ablations versus of the unaffected glass, which are circled in yellow, versus the defect area circled in white over that big brown smudge in the middle. They found no trace of uranium in the unaffected area or in the defect. You can see there on the right, thorium and uranium have got no concentration detected whatsoever. So we can rule out uraninite from the source quartz sand right there. What we did find, however, was iron at thousands of parts per million in the defect and single-digit ppm in the good or unaffected region, while sulfur occurred in the tens of parts per million in both regions. Now, if pyrite was the source of this defect, we would expect to find way more sulfur in the defect versus the unaffected area. So these results excluded both potential contaminants from the source quartz sand and helped the client narrow the possibilities down to debris from the production process. Now, that was a pretty classic material, silicate glass, but let's consider something a little bit more exotic. Our second case study today is concerned with measuring elemental abundance gradients for contaminants in a laboratory-grown gallium oxide crystal. The client is conducting ultra-wide bandgap research focused on gallium oxide as a promising material for high-voltage breakdown devices and deep UV LEDs. So for this study, two objectives here. We measured uncalibrated signal intensity for the elements chromium, silicon, zirconium, manganese, magnesium, iridium, copper, and iron in synthetic gallium oxide crystals like the one pictured. And second, we used that time resolved data to identify hot and cold spots, or area of high and low signal intensity in each crystal. Now, this is not true chemical mapping. It's essentially a proxy for that. Because we know the laser is moving over the sample at a fixed rate, how long into the analysis it is in terms of time is a approximate measure of where on the sample you are. So we used 5 scan line ablations per sample, and they were plotted parallel to the growth axis of the crystal as indicated by that yellow arrow in the figure. And the intention of locating the scan lines, which you can see between those red dashed borders, the point of doing it this way was for each line to pass through multiple zones of higher and lower contamination. That was the client's hypothesis. Now here we can see a single scan line zoomed in. And I want to use this to illustrate something in particular. Before we collected data, we did a pre-ablation or a cleaning ablation. So we ablated the same pattern, the same scan line using a 100 micron wide spot at pretty high speed. This is just a quick surface cleaning to scour away any contamination from handling or anything else. After that, we ablated a second time at a slower scan speed using a 40 micron spot. And you can see that circle in the middle there, it's 40 microns in diameter, indicates where that central laser ablation trough is located. Now, notably, those dark speckles in the image, those are not surface contamination. That's part of the crystal itself. So here we can see the time-resolved signal intensity data from a single scan line ablation. As indicated by the blue line, that dark blue squiggle at the top, the predominant contaminant throughout the growth axis of the crystal is the element iridium. However, iron was also found to exhibit strong signal intensity, but it's kind of hard to see it. You can see there's sort of a big green spike around 270 seconds or so, but it's obscured by iridium. So let's zoom in to see it more clearly. If we isolate the time-resolved trace to about 270 through 320 seconds post start of the ablation, we can see that iron mass 56 in green spikes just prior to an iridium spike in dark blue. This helped the client to determine that iridium was a continuous contaminant but variable in concentration, while iron is isolated in occurrence in the crystal but can show intensity comparable to iridium. So when iron's present, it really spikes quite abruptly, but otherwise it's nowhere near the abundance of iridium throughout the crystal. So one of the major advantages that I think this illustrates is that laser ablation, its time-resolved signal allows the analyst to detect and interrogate anomalies like intensity spikes. So this sort of data would be completely subsumed in a steady state analysis using solution mass spec or other types of mass spectrometry. So many of you may be more familiar with solution ICP-MS. So in this section, I'm just going to briefly expand on my earlier consideration of laser ablation capabilities with an attribute comparison and then a third case study. So my apologies, this one's fairly text heavy, but let's just work through this. It's just a couple of examples here that I think are pretty good at illustrating the strengths of laser ablation versus solution ICP-MS. They both have things they're very good at, and they're not necessarily the same thing. So let's just start with sample prep. So some of this we talked about before. For solution mass spec, some of the advantages, its liquid state makes it really easy to create matrix match reference materials. You can just dope in iron or nickel or whatever your matrix element is to create a matrix matched calibration curve. And you can add internal standards for data normalization to both your samples and your calibration curve. No problem, because it's all in solution. That's pretty classic wet chemistry. Now for laser ablation, you can't do that. It's much more challenging to have a matrix matched calibration or to add internal standards. You actually have to measure internal standards using a secondary technique in most cases. The strengths of laser ablation are those I mentioned before. Because it's not in solution, it's a fast, clean, and green approach with fewer opportunities for human error. There's just less time spent in the lab doing things to the sample. Now, in terms of the signal generated, solution ICP-MS uses a steady state signal, and that's ideal for compositional analysis of many elements with low uncertainty. You can run the same sample repeatedly until you run out of solution in different modes. So if you need to use kinetic energy discrimination to measure calcium, or an ammonia reaction gas to measure iron, or a standard no gas mode to measure boron, you can do all of those on the same sample, no problem. In contrast, laser ablation signal is time resolved. So you can try to use it to approximate a bulk analysis by doing an average of multiple scan line ablations or spots, or you can use spatially resolved analysis where you target individual features because you expect there to be differences. So for example, the case study with the defect versus the unaffected area, that's a spatially resolved analysis. Finally, data reduction. How do we turn signal into concentrations? So for a solution mass spec, this is very straightforward. These techniques are well established. The procedures have been around for decades. There's commercially available software, and it's frankly quite easy to understand how you do data reduction. It involves linear calibration curves in most cases. Now, laser ablation is both more powerful and a bit more finicky and requires more expertise to do well because you're looking at a time-resolved signal. So you can really burrow down into the nuance and details of what's happening if you have the skills to really visualize those data and see what's going on. So it's possible to select or to avoid parts of the time-resolved signal before you integrate it to get your concentration. And that graphical depiction of transient signal makes it easy to visualize instrumental drift and other anomalies. So an expert analyst can really see what's going on and whether they're getting consistent results over the course of a long analysis run. So moving on to compare solution and laser ablation, we're going to do a more complex case study. So this is the one I mentioned before that we're going to really walk through a pretty big job all the way. Now, this is personally my favorite case study in this webinar, and you might guess from my background why that's the case. So first, it's a geological and archaeological provenience study. We're talking about using what we call multi-element ratio fingerprinting by laser ablation to tell apart 3 sources of rock. So the goal here is provenience. How do you chemically differentiate among the rock deposits that ancient people used to make stone tools, and then figure out where the raw material for those tools was originally mined? So as an archaeologist and a geochemist, this is pretty exciting stuff. But also, as a chemist, it's a method development problem. Silcrete stone is a soil duracrust. Basically, it's just an ancient soil surface cemented together by silica. So it's sort of a garbage rock. It just gloms up everything on the soil surface, and it is really quite challenging to analyze. It's in no way homogeneous, which would suggest that a bulk characterization method like solution ICP-MS would be more appealing. But it's also a silicate rock. Silica is very hard to digest. It's a real challenge. So that's a problem for solution mass spec. And also, we're ultimately planning on using this for archaeological artifacts. It's typically not viable to undertake destructive analyses. These things belong in a museum. So this in turn favors a microanalytical and minimally destructive approach like ablation. So let's just see how these 2 methods, solution ICP-MS and LA-ICP-MS, compare for 3 silcrete sources in South Africa shown on the elevation map with those red dots in relation to the archaeological site of Pinnacle Point down on the coast indicated by the blue star. So our objectives here are to use minor and trace element concentration data, differentiate among these 3 geological deposits using statistical analysis, and then also secondarily to compare the ability of solution mass spec and laser ablation to achieve that first goal. How do we do this? We have 10 samples of rock from each source. Each sample was cut into 2 subsamples. One half was digested in acid and used for solution mass spec, and the other was embedded in epoxy and polished flat for laser ablation. Solution ICP-MS was carried out by our collaborators at Arizona State University using their thermoscientific ICAP-RQ, it's single quadrupole mass spec, and 3 replicate aliquots or subsamples of each digestion were analyzed. Laser ablation was carried out by me here at EAG Syracuse using our J200 laser and our Thermo ICAP-TQ ICP-MS, and I did 5 replicate scan lines per sample. So let's just jump right to the results. We can come back to how we got here later. So what you're looking at right now are 2 principal components analyses, or PCAs. PCA is a pretty straightforward multivariate data exploration technique. It's just widely used when you have to deal with more elements that can fit in just a bivariate plot on their own. So what you're looking at here are data points representing those 3 sources of silicate. So on the left, you can see 3 replicate aliquots turned into mean results. So they've been averaged, so there are 30 points on that plot, and you can see that the 3 sources indicated by the different colors and symbols are non-overlapping. They're very clearly discriminated among by the solution ICP-MS data using the 5 elements that were included in this PCA. Over on the right, now that's your laser ablation data. These are not averaged, so these are 150 data points, 30 samples times 5 replicate ablations, and you can see essentially the same result. We have non-overlapping groups of samples from each source, and using the same elements, they are spread apart the same way. So using lithium, copper, strontium, thallium, and lead, the same source discrimination was achieved with each technique. Now, this proof of concept study demonstrates that a microanalytical approach is viable, even for a really challenging and heterogeneous material like silicate. And now that we know it works for geological samples, we can hopefully apply it to archaeological silicate artifacts for determining their geological origin in a minimally destructive way. And this preserves the artifacts for museum display and for future research. So as I mentioned before, I skipped almost everything that happened in between the premise of that case study and the outcome. So for our final section, I want to return to case study 3 and put it all together in a project workflow, from sample prep all the way through to data processing and statistical analysis. So first, each halved sample of rock was embedded in an epoxy puck and ground flat to expose the sample surface. Once all the samples were prepared, I experimented with different laser settings and settled on those shown in this box at the top. Now, notably, this project used cleaning ablations, as I mentioned before. So no data was collected during the cleaning ablation, but the laser was scanned over the sample rapidly to remove any potential surface contamination from the embedding and grinding process. Now, how do you actually build a laser ablation run? What's the order of operations on the computer? So for data collection, laser ablation mass spec relies very heavily on the concept of sample standard bracketing. So rather than just running your calibration curve or standards at the beginning, you'll do that. So in this case, we used NIST 610, which is a silicate glass reference material. You'll run that 3, 4, 5 times at the beginning, run a QC, run your samples, but then at equal intervals, you interweave your reference material throughout the run. And by reanalyzing that calibrant over the course of the run, it allows the data reduction process to account for instrumental drift, which is important because for a long laser ablation run over 8 or 9 or 10 hours, you'll expect to see things change. Your background can become more elevated and it needs to be adjusted for. So this is what a sample looks like post-ablation. So there are your 5 replicate scan lines. And I like this image a lot because it really shows how challenging material this is. You can see there are darker red and orange areas where there's elevated iron concentration. There are cracks, there are voids. This is a really tough material to try to collect pseudo bulk analysis data on. But we see that it actually works. We were able to tell the sources apart. So even though this material is pretty far from optimal, that's actually why we picked it. Just see how far we could push using laser ablation on a non-ideal material. So lastly here, you can see that 100 micron diameter laser ablation trough. So I have this depth map right here. This is from microscopy after ablation, just to show you that that initial cleaning ablation, which used a 200 micron diameter spot, it has virtually no measurable effect on the sample surface. It's really scouring off barely anything. There's no measurable change in depth on that surface outside the bounds of the main data collection ablation, which is pictured as that trough right there in blue and green. But that was only half the story. Data reduction, processing, and statistical analysis is of equal importance to sample prep and data collection. So first, data reduction. I mentioned earlier that semi-quant data can be very powerful. Well, that's what we collected here. This is not fully quantitative data. We did in fact use a matrix-matched external calibrant, so that NIST SRM 610 is a silicate glass, which is the same matrix as a silicate rock, but we didn't use an internal standard. Now, typically for geological material like this, what you would do is you would measure your samples using microprobe or SEM EDS or even LIBS to measure silicon concentration or another major element, and then use those values as your internal standard. That adds to the time and the cost of this job. And for our objectives here, we don't actually care what concentrations are. We just want to use those concentrations and the relationship among those elemental variables to tell apart the sources. So semi-quant data is just fine. So we didn't bother with an internal standard here. So now that you have your semi-quant data in parts per million, you have to process that data and clean it up a little bit. So first, were there any below detection limit values? Because if you have a value or concentration that's below the limit of detection, it's a nonsense number. You can't actually use it for data analysis. As I mentioned before, though, silicat's sort of a garbage rock. It's just full of everything. It's chock full of trace elements, so not a single one of the 40 some odd elements that we measured had a below LOD value. So none of those values were censored. So after looking at LODs and any BDL measurements, what about outliers? I mentioned before, they're voids, they're cracks, they're inclusions, so there are bound to be some outliers. So in order to identify a pretty conservative number of outliers, we used a k-nearest neighbors multivariate outlier detection and eliminated 5 out of those 150 results. So that's a 3% rejection rate. That's very conservative. I like to keep as much data as possible. But now what do you do with these results before you put them into a PCA or another statistical analysis? Transforming them is really, really important. So principal component analyses are really susceptible to being overwhelmed by major variations in magnitude. So what I mean is if iron is measured at 3,000 or 10,000 parts per million and lithium is at 20 parts per million, you can get some pretty biased results. So there's some ways you can try to account for that and minimize that bias. And transforming your data this way is a major one. So first, we standardize all of our trace and minor element data to the silicon matrix. So we measured silicon, and then we just divided all of our elements by the silicon concentration for each scan line. So this is almost like a pseudo-internal standard. It's doing basically the same thing as a true internal standard. It's normalizing for ablation yield. And then subsequently, you log 10 transform these ratio variables to make them even more constrained in their range of magnitude. So now that you have your data in this log 10 ratio form, we want to narrow down the variables. We don't want to try to put 40 variables into a PCA. That's just too much going on. So I use the approach bootstrap forest partitioning or decision trees in the software program JUMP or JMP to rank variables as predictors of source group. So what this does is give you a prediction of which variables will work well on their own or in combination to tell apart those 3 sources. So you specify, we have a categorical discrimination problem, which variables are useful for telling apart those 3 categories. So once we narrowed it down to the top 10 or 15 variables, you just build your PCAs in multiple iterations. You try one, you try it again, and you try different combinations of variables until you have the minimum number that you need to successfully tell apart your sources while still accounting for most of the variation in your data set. So in this case, we have our final PCA using 5 elements in that log 10 ratio transformed format. So having covered that case study, talked all about laser ablation, as we start to wrap up and move toward the questions, I just want to talk about a few other techniques that we offer at EAG that I think are really great complements to laser ablation. If you come to us asking about laser ablation, I encourage you to ask about these techniques as well. They might be great complements. They might be better for your particular application. So let's just touch on these quickly. So scanning electron microscopy, energy dispersive X-ray spectroscopy, or SEM-EDS, can be used for the rapid imaging of discrete surface features and preliminary characterization of major and minor element composition. So you can also follow that up with laser ablation in order to quantify your elements that are present with lower detection limits than SEM-EDS. But that technique is a great first step if you need to image something that's not optically visible, if it's a chemical gradient or if it's an inclusion that you can't see with the naked eye or under optical microscopy. Doing SEM-EDS first before laser ablation, great place to start. Now, I mentioned earlier that our Applied Spectra J200 laser is a tandem system. What that means is that EAG can uniquely offer tandem laser ablation ICP-MS and laser-induced breakdown spectroscopy, or LIBS. Now, that means we can simultaneously measure analytes of interest with high precision and low limits of detection using mass spec, and also rapidly survey all elements present with optical spectroscopy via LIBS. You can actually even use LIBS in some cases to measure an internal standard element and then use those values to obtain fully quantitative laser ablation mass spec data in a later step. And finally, I would be remiss if I did not mention glow discharge mass spectrometry, or GDMS. It's the major technique that we offer here in Syracuse. This is an ideal survey technique for full scan. When you need to measure 40 to 60 elements on a solid sample, this is typically where you want to start in most cases. However, it uses a much bigger spot size than laser ablation. So LA-ICP-MS can be used subsequently to either quantify particular analytes of interest using an independent technique that's completely different than GDMS, or if you suspect that there is spatial variation in your samples that is actually quite important to your goals and your objectives, and you need finer resolution spatially than GDMS can offer, then this might get shunted over to laser ablation instead of GDMS or in addition to it. So just to finish up now, you've heard all about laser ablation, seen some pretty cool examples, I hope, but why would you choose to work with EAG? We're not just a commercial service laboratory, we're a lot more than that. I think the top reason I have to mention is that client confidentiality is core to this business. Whether it's closely held IP, sensitive failure analysis projects, or work with regulated materials, your interests are our interests. On the other side of that coin, we also proactively seek out collaborative endeavors with academic laboratories and instrument manufacturers and share the outcomes at conferences and public webinars like this one. So basically what you're getting with EAG is the best of a university lab and a commercial lab and the contract research organization all in one. We're a global leader for materials testing services with a broad range of instruments, expertise. This positions us to take on even the most challenging materials science, analytical chemistry, and engineering related issues. So in closing, thank you all for joining me today.